Welcome everyone! I'm going to discuss the thermal management aspects for a space implementation of the Qormino QLS1046 space module. It is often a challenge for designers to manage the heat dissipation of heavy computing electronic systems embedded on a spacecraft. Today, the focus is on the cooling strategy of the QLS1046 space module. Before jumping to the topic, we need to make a stop on the QLS1046 space construction. Teledyne E2V QLS1046 space is made of a LS1046 space processor, a space DDR4, and the required passive components. All the components are installed on a substrate with a BGA grid underneath. In all this, the components that are dissipating heat are the processor and the DDR4 memory. And the processor is the greediest by far. First, you need to estimate the power consumption of the LS1046 space processor, which can be done based on the power estimation guide. For instance, this figure shows the power consumption of the device when operating at 1.8 GHz, depending on junction temperature and number of core used. In normal operating conditions, the power consumption of the processor is expected in the 7 to 15 watt range. For the power consumption of the DDR4, a calculation spreadsheet is available, and the typical power consumption ranges from 1 to 1.5 watts. Now that we have discussed about power consumption, let's focus on how to dissipate the heat. The cooling of a Qormino QLS1046 space is not very different from the cooling of any other component in space. For both the DDR4 and the processor, thermal models and thermal resistance values are available to perform the thermal analysis. In most applications, the memory has a limited power consumption, hence it does not always require heatsink on top of it. On the contrary, because of the high power density of the LS1046 processor, it needs a heatsink most of the time. In space applications, the heatsink is usually an aluminum or copper plate placed on top of the component. Copper thermal straps are then used to propagate the heat toward the spacecraft mechanical structure or directly to the cooling panel. For the cooling strategy, there are two cases to consider. If the heat produced by the DDR4 can be dissipated through the PCB, a heatsink is not required for the DDR4 and only required for the processor. In that case, the heatsink is sized as if the processor was used in standalone. In the case where the DDR4 also requires additional cooling, the recommended solution is to use a heatsink covering both devices. Since the processor is taller than the memory, the difference has to be compensated either by adding a thermal gap filler or by adjusting the thermal plate thickness as shown on the figure. When the heatsink covers both devices, the thermal analysis is a bit more complex, and Teledyne E2V has made some simulations in different cases to help customers size their cooling system. Simulations have been made with a power consumption of 10, 15 and 20 watts on the LS1046. For the DDR4, the simulation is performed only for a power consumption of 1.5 watts. The operating temperature applied on the PCB on which the QLS1046 space is installed is set to 60 degrees or 80 degrees during the simulation. In terms of cooling, a convective heat flux of 2500 and 3600 watts per square meter per Kelvin is applied on the aluminum plate used as heatsink. This represents the heat dissipation capability of the cooling system. Overall, 12 simulations have been performed for the different conditions. The detailed results are presented in the dedicated application note QLS1046 Space Thermal Management. In this video, I'm going to stop on two simulation cases. The first case is a simulation in a best case scenario where the PCB operating temperature is 60 degrees and the processor consumes 10 watts of power. In that case, even with a cooling flux of 2500 watts per square meter per Kelvin, the junction temperature of the device remains low, not exceeding 80 degrees for the processor. The second case is a simulation in a worst-case scenario where the PCB operating temperature is 80 degrees and the processor consumes 20 watts of power. The cooling flux is set to 3600 watts per square meter per Kelvin to prevent from overheating and to keep some safety margin with the maximum junction temperature. In that case, the processor operates at about 115 degrees C. In all simulations, the DDR4 junction temperature remains far below the processor junction temperature, which means that the primary design goal for the thermal management is to cool the processor, and consequently, the DDR4 will be cooled properly. What the simulation also shows is that a 3600 watts per square meter per Kelvin cooling flux is sufficient to cool the QLS1046 space in the worst conditions. In order to properly size the cooling system in your specific application, the first step is to estimate the power consumption of the QLS1046 space. Based on the power consumption and your environmental conditions, you need to find the nearest operating point in the sets of simulations performed by Teledyne e2v. This is found in the application note QLS1046 space thermal management. Then, depending on the maximum desired operating temperature of the device, the required cooling flux can be determined. And finally, you can size your cooling system to reach the target cooling flux. Thanks for watching. Don't hesitate to get in touch with us if you need the application material or if you have questions.